we are not concerned about the deterministic experiments in this course. We are concerned about non-deterministic. So what is non-deterministic? Non-deterministic experiment is that even if we fix conditions, underlying conditions for conducting the experiments, the outcome cannot be predicted in advance. So for example, you are studying in this particular class, okay? So you have procured your tablet or laptop or your smartphone or desktop, and you are going to attend this class. And even then, and you fix that the teacher is there in time, and you connect through Microsoft Teams. But it is not sure whether the connection will be done. Like you will be getting, there will be some students who will complain later that I had a network problem and it could not be connected, and so on. So for example, all of you are studying in this course, and maybe all of you, many of you will be studying, say, 2 hours per day for a particular course. And when you appear in the exam, you do not know what would be your performance, whether you will do very well, whether you can answer all the questions or not. So even if the difficulty level is also announced in advance, you know the previous year's question papers, whatever be that, but ultimately the performance cannot be predicted. And same thing is true about most of the things which happen in the real life, whether you consider longevity of a person, the survival time from a disease, the amount of rainfall, the climatic conditions, the agricultural production, the rate of economic growth, all of these things, whatever macro level or micro level things you consider in the universe, all of them, they have certain undeterministic or non-determinacy in their behavior. Now the subject of probability and statistics is developed to study such non-deterministic phenomena. So as I mentioned to you, the development of the modern probability theory started from gambling games, because people thought that that is the true non-deterministic thing. That means if you toss a coin, you do not know whether a head or tail will come. If you draw a card, then which card you will get, or if you toss a dice, then what you will get. So people thought that these are the true examples of the non-deterministic experiments. However, it turned out later, because of course that was 17th century and that was the time of the Newtonian physics. So people thought that ultimately the laws of physics will be universal, and once the laws of physics are known, then everything will be determined. Later on, it turned out, when the advent of quantum mechanics, that yes, things are non-deterministic. Even at a very, very microscopic level also, things are non-deterministic. That means even the movement of your electron and so on, that is non-deterministic. So then we discuss random experiments, and when you have a random experiment, we have a sample space. Okay. The set of all possible outcomes of a and we usually use the notation capital Omega or S, etc. These are the notations that are used for defining or writing down a sample space. So let us consider some trivial type of examples. Okay. So let us start with the simplest, tossing of a coin. So you can have the sample space, either head comes or the tail comes. You can have, say, tossing of a dice. And if we look at what is the uppermost face, then you will have the numbers 1, 2, 3, 4, 5 or 6. If you consider, say, drawing of a card, then what could be the sample space? Well, when you draw a card, and if we look at a color, we want to see the color. Then color of a card is either black or red. If we want to see the denomination, okay, then it could be heart, a diamond, club, or spade. I want to confirm whether you can see what I have written. Is it getting transferred to your screens?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes.
Okay.
Yes, sir.
We may like to see what is the value of the card. For example, it could be ace, 2, 3, and so on. For example, 10, or it could be jack, queen, or king. Or it could be purely what is the card. So in that case, you may have to like say it's a 1 of heart, or it is a 2 of heart, or it's a king of heart, or it is a diamond ace, and so on, diamond king, club ace, or club king, or it is spade ace, or spade king, and so on. So you may have the full description. Of course, we may write in the uniformity. 13 I am writing here. So let me put here hello. Yeah, actually I'm in a class. At what time you want to keep? Because I will have to send the link then. 4 o'clock. Oh. Okay, then I will send a link. Or you can send a link, no problem. Okay, you can just send a link, no problem. Because actually I'm in a class and it will be over after some. Okay. Okay, yeah. So actually this example shows that even if, see, I am talking about drawing of a card from a deck of cards, but I can describe the sample space in four different ways, depending upon what is my interest. If I am interested in the color, then this is my sample space. If this is my interest to see that what is the denomination, then I will use omega 2. If I am interested in the value of the card, then I will use omega 3. If I am interested in the actually what is the card, then I will use omega 4. So 4 different ways of describing this one is there. Let us go to a little bit more practical examples. These are the examples which were there when the gambling games were there. Let us look at other things. So for example, if I look at say birth of a child, suppose I am looking at birth of a child, okay, and then I look at the gender, for example. If I am interested in gender, then it is a boy or a girl, okay. If I am interested in the weight at birth, okay, if I look at the weight at birth, then it could be say anything, say from maybe we put an interval, say 0.5 kg to maybe 3.5 kg. So it is in kgs, okay. If I am looking at the weight at birth, if I look at say height at birth of the child, so in a different ways we can write down the sample space again. If I look at say longevity of an adult, okay, of a adult human. So if I look at the longevity of an adult human, and if I say what is the adult, then suppose we put the age 18 onwards, then it is 18 to, and we put some upper limit, say 120, because we may not see a person who is of more than 120 years. So this could be the sample space. if I am looking at, say, amount of rainfall during, say, monsoon, say in one place, say for example, I say in a city of Mumbai. Okay, so it will be in certain centimeters. So for example, it could be from say 30 centimeters to maybe 200 centimeters. In the case of sometimes there is a super rain days are there. So you can see here that the sample space means we can describe depending upon what is our interest here. What is an event? So any subset of a sample space is an event. Okay. Now this immediately explains that in any given random experiments, the number of events can be very large. As you know, if I am considering a finite number of outcomes, then in the finite number of outcomes, so if I have a finite number of outcomes, say n in number, then the number of events, the total number of subsets of a set containing n elements can be 2 to the power n. So from here itself you can understand, and now you can see that we have also the sample spaces where you have infinite number of outcomes. For example, 30 to 200. So it is an interval. It has uncountably many elements here. Similarly, longevity of a person, weight at birth. So these are all uncountably many things, and therefore the number of subsets will be infinite here. So therefore, if we properly define a sample space,
Sir, you are muted.
can you hear me now?
Yes,
Yes, sir. Now we can
yes,
hear you.
yes.
And this sheet
Yes,
is
sir.
visible, no?
Yeah.
Okay,
Yes.
let me put it little bigger. Okay. Okay. So then the question comes that is it feasible practically to consider all types of events when we are discussing the probabilities? Okay. So okay, we will come to that thing. Okay, that which events to consider, whether all events should be considered. So as you can see here, the number of events becomes very, very large. Okay, because if I have an infinite interval 30 to 200 centimeter, then how many elements are there in the there are uncountably many, and therefore the number of subsets is also uncountably many. So we talk about then various kind of events. So phi is so phi is a subset of every set, therefore phi will be always there. So this is called an impossible event. Okay, the event which cannot occur. So for example, if I say tossing of a coin and I will say that I will get 3. So 3 will not come because there is no 3 if you toss a coin. You will get either head or a tail. Similarly, if I toss a dice and then I say that there will be 15 coming there, so 15 cannot come. If I consider say weight of a newborn child and if I say the weight is 100 kg, then this is not possible. Okay, so these are all examples of impossible events. And of course, you can have the full omega. Then full omega is also a subset of omega, so that is called a sure event. Okay, if I have to toss a coin and I say either head or tail will come, then it is a sure event. Then you have the concept of union. Okay, so we know that if E is an event and F is an event, so these are sets. So E union F denotes a set. Okay, this means happening of either E or F or both. Okay, so now we can extend this concept. In place of one, we can have union of several. So for example, I can have A1 union A2 union AN, which we can write as union of AI, I is equal to 1 to n. This means occurrence of at least one AI. Okay. You can actually consider even union of infinite number of events also. Okay, so these are all allowed. So union of sets is well defined. Since I am saying an event is a set, so union of the sets is well defined. In physical terms, it means occurrence of any one of them, at least one of them. So if I say union of A1 union A2 up to AN, then it means that A1, A2, A3 may occur, A1, A2, A4 may occur, or A7, A11, A13 may occur, and so on. It can be union of any of them, any number of them. Similarly, we have the intersection. So intersection in set theory, you mean the common elements. Okay. So it means that both A and E and F will occur. So it means simultaneous occurrence of both E and F. So you can have again more than 2 also. This means simultaneous all AIs. So again, it means simultaneous occurrence of an infinite number of events. So these are all defined because now you have the concept of a set connected to any description of any event. If the union AI is equal to omega, that is the sample space, then A1, A2, AN, they are called exhaustive events. If A intersection B is phi, then A and B are called disjoint or mutually exclusive events. So you can have, if A1, A2, AN are any events and AI intersection AJ is phi for I not equal to j, then these are called pairwise disjoint events. And of course, you have the concept of complement. So if A occurs, we denote it by the set A. So if A does not occur, we will denote it by A complement. So this will be called not happening of A. So any of you would like to ask any question at this point? I have told certain very basic terminology related to the description of events, the experiment, the sample space, and also what is the notations or notations of union, intersection, etc., referring to concept of happening of events. So these things I have described. So do you have any questions on this? Then I can proceed further. I would like to hear from any of you.
No, sir.
Okay. When I am writing down, you can see what is being written. The sheet is visible to you.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So yeah. I mentioned to you 3 names yesterday. Laplace, von Mises, and Kolmogorov. Okay. Each of one of them is credited with giving a definition of probability, which we can consider as methods of evaluation of the probability. So we start with the first one, that is the Laplace, the French mathematician, famous French mathematician, physicist, and so on. So he gave what is known as classical definition of probability. This is the definition which you studied in your school also for solving problems related to coin tossing, dice throwing, and so on. So the definition is very simple. Suppose a random experiment has n possible outcomes which are mutually exclusive, exhaustive, and equally likely. So for example, in the tossing of a dice, we have 6 possible outcomes. 1, 2, 3, 4, 5, 6. So if one occurs, 2 cannot occur, and so on. So they are mutually exclusive. We are counting all of them, that is 1, 2, 3, 4, 5, 6. And if it is a fair dice, then we are saying they are equally likely. That means one is as equally likely to occur as 2, as 3, as 4, as 5, and as 6, and so on. Okay. So if there is an event A, let m of these be favorable to happening of an event E, then the probability of event E is defined by m by n. Is there any student who does not know this definition? All of you know this definition? You have done it in school.
Yes, sir.
Okay. So all of you know, I have again repeated it because this can be considered as a method of evaluation of the probability when these conditions are satisfied. That means there are n equally likely, mutually exclusive and exhaustive outcomes, and then you want to find out probability of certain event, then you just look at the favorable number of cases. So for example, if I say two fair dice are tossed, what is the probability that the sum is 5? So you look at the possibilities, if two dice are tossed, then the total number of possibilities are 36. And if I am asking the probability of 5, then you are looking at immediately 1, 4, 2, 3, 3, 2 and 4, 1. So there are 4 favorable cases. So the probability is 4 by 36, that is 1 by 9. That is the way you solve this kind of problems. Okay, the purpose of giving this definition is not just to tell you this method. The problem is that this method is not enough to solve almost every problem which appears in the real life. So if somebody is infected with a disease and I ask the question, what is the probability that he will recover? You cannot answer this question from this one. Suppose I say I got a fever and what is the probability that I will recover in 3 days? This question cannot be answered using this definition. So suppose I say, what is the probability that the food grains production in the country this year will be, say, 10,000 metric tons? So can you answer this question using this? No. Because when we are discussing the random experiment should be of a particular type. Then only this definition can be applied. So what are the drawbacks of this definition? The first is that n need not be finite. Okay, because all the examples that I have told just now, they don't have finite n. Like if I say, what is the agricultural production, then this is an infinite set. If I ask you the days of curing, then these are all infinite sets. Okay, the definition is circular in nature, because here we are actually defining the probability, and in the probabilities definition itself I am using the word equally likely, which means equal probability of occurrence of those outcomes. So for example, 1, 2, 3, 4, 5 and 6, they have the equal chance of coming up. That means I already know the probability. So this is, the definition is circular in nature. Okay, because it uses the term equally likely, which means outcomes are with equal probability. Okay, so what is the other method? What can be the other thing if we have infinite? So if I want to find out that if somebody gets a cold, what is the probability that he will get cured in 3 days, or what is the probability that he will get cured in 4 days, and so on. So a practical scientist will look at the data available with, say, a doctor or in the community, that the number of people over a period of time who are getting a disease, and then how much time they are taking to get cured based on the medicines that are being given. So you look at the ratio. So for example, if I am looking at the birth of a child, and over a period of time I want to find out what is the probability that the next child that is born will be a boy or a girl, and you say that it will be half. So how that answer is given? It is based on overall, in the overall population, how many births are of boy child and how many births are of girl child. So if you look at the data is approximately 50-50, then you give the probability half. So this concept was generalized by physicist von Mises, and then it called empirical or relative frequency definition of probability. So it is by the physicist von Mises. Of course, I mean there were various versions since he put it on a formal framework, so we name it after him. Otherwise, the concept was already there in practice. So, if a random experiment is repeated n times and an event E occurs an times, okay, then probability of E is defined as limit of an by n as n tends to infinity. Okay. So you look at the long-term ratio of the occurrence which is favorable to that event. And so even if say for example there is a coin and I don't know whether it is a fair coin or not, it could be that it is more loaded in the side of head, or it could be more loaded in the side of the tail. So what I do, I actually consider the outcomes and then I look at the ratio. Suppose the tossing is done 1000 times or say 200 times, and then we look at, so if we find out that suppose out of 100 trials, say 75 times it's a head and 25 times it's a tail, then we will associate the probability as 3 by 4, that is 75 by 100 for head. Of course, you may say that it may change if it is done more number of times. So in place of 100, suppose we make it 1000, and it happens that in place of 750, it is now 780. So then the probability, you will say it is 0.78, it is not 0.75. The idea is that if an experiment is having a pattern, then over a large period of time, the probability or this limit will stabilize. So it will not fluctuate. So if you are saying that if I make it 1000, then it will be slightly more. Yeah, so it can be, but over a long period of time, this value will stabilize and there won't be much change. And that is why we are saying it's a probability. So for example, if you look at few trials of launching of the satellites. So for example, the launching of satellites started in 1957 with the launching of Sputnik from USSR, or the earlier Russia. And then there used to be a lot of launchings and there used to be a lot of failures. But over the period of time, if you look at now, for example, India, In India, it started in 1978, and after that, there used to be a lot of failures. I mean, like if 3 launches are there, there will be 2 failures and 1 will be successful. But now you see that every year India is launching something like 100 to 200 satellites, and none of them are failures. So slowly that probability has stabilized. So what is the probability of success of a successful launch? So then you look at the ratio, and then you can associate a probability something like 0.99 or something like that. Okay, so let me just give a practical example. Suppose I consider a tossing of a coin, and so as I said, it need not be a fair coin, and we look at the coin which may be say 3 times more loaded in favor of head compared to tail. So you will say that the probability is 3/4. Okay, let us look at a hypothetical experimental outcome here. Suppose we say H H H T. So I'm just putting in a sequence. It need not be in sequence, but since it is a classroom exercise, so I will put it like this. Okay. So 3 heads followed by a tail. Let us see whether this definition will give me 3/4 as the answer or not. Let us look at the event A, that is the occurrence of head. We want the what is the probability of A? Okay, we want this probability. So I need to calculate this AN by N. See, we have to look at this AN by N. Let us see, in one trial you get 1 head, so the ratio is 1/1. In 2 trials you get 2 heads, so it is 2/2. In 3 trials you get 3 heads, so it is 3/3. Then in the 4th trial you got a tail, then it is 3/4. That is the favorable number of outcomes to the event A out of the total number of trials. Okay. Again you get a head, so it becomes 4/5, 5/6, 6/7, and then next number will be 6/8, and then again it may follow like this. So it will become then 7/9, 8/10, 9/11, 9/12, and so on. We want to find out what is the limit of this. Okay, writing down these numbers will not give me the limit, so I want to find out the limit. Let us apply this definition. So let us use little bit of mathematical argument here. See, what is the kind of numbers? If you look at every fourth number is of the type 3/4, then you are getting 6/8, then 9/12. So it is actually 3/12, 3/4. So this number is actually, we can write it as 3k/4k if n is of the form 4k. That is, every fourth outcome gives me 3/4. So the number an by n is actually of the form 3k/4k. Now if we look at one before that, then what is the number? It is 4k minus 1 and 3k. So for example, if you look at this one, if you look at this one, if you look at this one, then it is 4k minus 1 in the denominator, and you have 3k. So if n is of the form 4k minus 1. Likewise, you can write for the next one also, this one, and this one also. What it is? It is 4k minus 2, 3k minus 1. So n is of the form 4k minus 2. And of course, the first one then, if it is of the form 4k minus 3, then it is 3k minus 2. This is valid for k equal to 1, 2, and so on. Is this description of an by n clear to everyone?
Yes, sir.
Now you can see this an by n I have actually broken up as 4 subsequences. And if you look at the limit here, for each of the subsequence, the limit is 3 by 4 only. Whether you consider 3k by 4k minus 1, what is the limit? It will be 3 by 4. If you consider the limit of 3k minus 1 by 4k minus 2, the limit is 3 by 4. If you look at the limit of 3k minus 2 by 4k minus 3, the limit is 3 by 4. So, limit of an by n as n tends to infinity is 3 by 4. So, this is the probability of head here. So, this is just to show you a practical application that actually in a long run, this ratio an by n, it will stabilize, and that ratio will be the probability of that particular event. Okay. So, this is actually the most well-known and practical method of assigning the probabilities of various kind of events. So, I mentioned to you, so you will be wondering that what is the probability that you will get an EX grade in this course. Okay. So, then what you do, you look at the data in past 20 years and you see that what percentage of students they got EX grade in the course probability and statistics. So, you may look at, say for example, this particular course, or you may also look at the course, other courses which are taught by me or any other particular teacher. So, you can look at what is the ratio or proportion in which he allocates the EX grade. So, it has nothing to do with the ability of the student and other things, because here we are not getting into the scientific analysis of this. We are looking at the empirical evidence that what has happened. So, as I mentioned that you are looking at day-to-day events which are happening. So, for example, the government every day presents the COVID data, and then they give the COVID recovery rate and the mortality rate. And it is true for countries of all countries of the world. And there you can see that they will say that the probability of recovery is, say they are saying 0.99 or 0.97 depending upon the different countries. So, what has happened? Over a period of time, those values have stabilized. Okay. So, in India, for example, the fatality rate is now just 0.1 or something like that. From the initial, it was like 3 or 3.2 or something like that. But slowly it has stabilized to a very small number. What could be the practical drawbacks of this definition? For example, it is difficult that see, if you don't have the historical data or the empirical data available with you, then you cannot apply. In that case, you will base your decision only on few available observations, and that may give a misleading picture. So, that happens quite often while formulating the government policies and other things, because they take a small sample which may not be representative, and then they make a decision. So, for example, you can look at certain framing of a new law. So, they will say, okay, we took the opinion of large number of people, this is the ratio who prefer, so we give this law. But then they might not have done the sampling correctly, and the data may not be actually correct. So, one drawback is that the actual observations on the random experiment may not be available. Second thing is that see, when we have ratio an by n, you know there is a mathematical ratio, and you know the limits also. So, for example, we find out the limits of large number of sequences. So, if I put say sin n by n, or if I consider say sin 1 by n divided by 1 by n. So, n times sin 1 by n. So, as n tends to infinity, this goes to 1. Okay. But does it mean that the event is sure? No, because there are certain number of cases, because n into sine of something, it will be actually less than n. So event is not sure, but the probability is 1. What does it mean? Physically, it means that it is more likely to happen. That means it almost always happens. Sometimes it may not happen. But even then, this definition will allocate probability 1 to that kind of event. Similarly, it may also happen like I put log n by n. So log n by n goes to 0 as n tends to infinity. So out of n trials, the event may occur log n times, which is much smaller, but event actually occurs. But the probability that if you calculate using it will give you 0. For example, rare events like tsunami or any other kind of natural disaster, or even this disease which has occurred. So they say that such a disease occurs once in 100 years and so on. So it is rare, but it actually occurs. So the probability, if we are assigning 0, it is not fair. But this definition will allocate probability 0 to it. So the probability of an event may be 0, but the event may be occurring. For example, an is equal to say log n. So then an by n goes to 0. Similarly, an event may not always happen, but the probability may be 1. For example, an is equal to n sine 1 by n. So these are just two examples where it is not satisfying the thing. Okay. Anyway, so this is considered a practical method of evaluation of the probabilities. Now, if we go to scientific definition in mathematics, see, mathematical structure is that it should never fail. So, for example, if I say certain thing is a set, so how the set is defined? Then the set is defined, then that definition is valid for all sets, isn't it? If we consider, say, a certain definition of a limit of a sequence of numbers, then that definition is valid all the time. So it's a definition. So you say that an tends to a, then you say that for every epsilon greater than 0, there exists an n such that mod of an is less than mod of an minus a is less than epsilon whenever n is greater than or equal to n. So that means the number comes closer. See, it doesn't tell you how to find that limit, but it gives you a method, a definition which is universally applicable. So we talk about continuous function, we talk about differentiability and so on. So these are all definitions which are universal in nature. Okay. So after looking at these methodologies of evaluation of the limits of, the probabilities, then in the scientific circles, it was thought that can we have a mathematical foundation for this? So then we got this axiomatic definition. I mentioned you the third name yesterday. It is by A.N. Kolmogorov, the Russian mathematician, in 1933. This is based on a little bit of formal structure. So if I consider let omega be a space. So space means a set, but I will call it a space because I am using the terminology sample space here. So we can call it sample space here just for clarity purpose here. And we consider here let B be a set of events. Okay, so we will call it a class of events. Okay, class of events. That is B is a class of subsets of omega. Because for what purpose we will define the probability? We will define the probability for certain events. Okay, so events are subsets of the sample space. As I mentioned to you that all subsets, if you consider all the time, then it may be too large a number. Even in something as simple as like if I consider tossing of a dice, it is 1, 2, 3, 4, 5, 6 elements are there. But if I consider how many subsets are there, it is 2 to the power 6, that is 64 subsets are there. Okay, and if we increase the number, suppose I say I take 10 elements, then it is 2 to the power 10, that is 1024 elements, and definitely the number becomes unmanageable if we are looking at countably infinite or uncountably infinite set of elements. Now, to become practical, is it necessary to consider everything? Do we consider all the events? It may not be necessary. So we give a structure and we may consider only those events which are relevant to our discussion. And then we define the probability structure for that only. Okay. So script B is a class of subsets of omega satisfying the two conditions. One, E belonging to B implies that E complement belongs to B. And second is that if E1, E2 and so on belong to B, then union of EI belongs to B. Okay. Then B is called a sigma field or sigma algebra of subsets of omega. Okay. A consequence of this definition is that B is closed under the operation of countable intersections, and of course it is already closed under the unions, it is closed under the complementations, it is closed under the differences, and so on. That means if I am considering any two events, I may be interested in then simultaneous occurrence, I may be interested in the occurrence of at least one of them. So if I am taking events say A and B, then I may be interested in A complement union B, I may be interested in B minus A, and so on. I may be interested in any combination of two events, three events, four events, and so on. So this sigma algebra actually takes care of that. So although I may not consider all the events, but I can consider a certain number of them which are relevant to our study. So this sigma algebra, it is a mathematical structure, it is helpful for that. So we have then omega, that is the sample space, and we have B, which is a sigma algebra or sigma field of subsets of omega. So this is called then event space. we will call then this omega and B as a probability space if it satisfies certain property. I will stop today's class at this point, and in the next class I will give the axiomatic definition and what are its consequences, and then certain problems we will do in the next class. And I will be uploading these lectures also, so that you can also read them later. Is that okay?